Hi everyone, today I'm going to go through the micro lesson on the use of Gauss Law, which is a very important part of Olympiad physics. It will be something that we can apply to many situations, simplify many complex situations, but it has its limitations. So we'll discuss these few things as we go on. But I'm going to start off with something that we're going to use the conventional method. I'm going to show you how to do it using proper integration. And you see for yourself how Gauss law simplifies the work process. So let's begin with what we know, which is gravitation in the past lesson. In the previous lesson, we know that if you have a mass, you have at this point a G, which is the gravitational field strength, which is Gm upon r squared. This is the gravitational field strength. If you have a charge, which is plus q, at this point, distance r away, it produces an electric field, which the field strength is measured by kq upon r squared, where k is 1 upon 4 pi epsilon naught. This is what we call the permittivity of free space. Now, this has a value of 8.85 times 10 to the power minus 12, whereas this has a very nice value of 8.99 times 10 to the power 9. So the electric field strength, the form for the electric field strength is rather similar to the gravitational field strength. So that's something that is good because we don't have to remember, you just remember the form and it'll help you remember the equation itself. So they are both of the same form. We're going to apply this to something which we call a line charge. And you will see for yourself how this can be applied to, this equation over here can be applied to many situations. It is the fundamental. It is really the very basic, the basics of electric field. Everything in this world can be broken down into point charges. So this is rather fundamental. So let's start off with the fundamentals. Imagine that I got a line charge over here. The charge per length is equals to rho. Let's call this rho. And I got a point over here where I want to find the field strength due to all these positive charges over here. And this is of distance L away. Let's consider the effect of this section of the charge on this point over here. So field strength always point away from the positive charge. Therefore, the field over here due to this will be pointing this way. Let's call this x and this angle theta over here. Let's consider on the other side. Can you see that on this side, which is of equal distance away, it will also create an electric field E of the same strength. And the horizontal component of these two fields cancels out because they are symmetrical. So this cancels out with this. Is a vector quantity because it's related to force. But the vertical component of both of them adds up. So therefore, the resultant E field at this point due to these two will be equals to 2 times of the small little E field due to each of them. Let's call it E then. And multiply by, if this is theta, the vertical component will be sine theta. Cool. So let's further break down this E over here, which is K due to this small little charge r squared sine theta. Now r squared is the distance from this point over here to here. Therefore, it is equals to 2k dq upon x squared plus L squared. Sine theta is equals to opposite over hypotenuse, which is going to be L divided by L squared plus x squared. And dq over here can be broken down into 2kl, the charge density times the small little length. So if you put everything together, it's going to take this form. So that is the small E field due to these two small sections of the wire. And obviously, you're going to see that integration is going to come in. Because this is just a small section, how do you find the collective effect due to the whole wire? So this is what we're going to do. We're going to integrate dr, which will give you resultant field. It's going to be the integral of 2k rho L dx upon L squared plus x squared cubed square root. Now, if you look at this integral over here, the question is what's the limits? We're not integrating from minus infinity to infinity because we have already multiplied, we have already come up with the expression over here taking into account the field due to these two. So all we need to do is to integrate from 0, where x equals to 0, to infinity. Alright? So we can bring this out, 2k rho L dx integral of L squared plus x squared cubed square root integral from 0 to infinity. And there's a standard integral that you can use. I think it is this. Let's just do a quick check to see whether it's correct. X upon a squared, not a. So therefore, this a over here is L. L squared bracket x over x squared plus a squared square root 0 to infinity. Now if you substitute 0 over here, it will be 0, so it's neat. Infinity over here is a bit trickier, but if you substitute infinity over here, this will be negligible compared to this. So x squared plus a squared will be approximately x squared, and square root of x squared is x. So x cancels out. So if you substitute infinity over here, it will be 1. And if you substitute over here, it will be 0. So it's 1 minus 0, which is 1. Therefore, this whole integral over here is just this, which is equals to 2k rho upon L, which is rho upon 4 pi epsilon naught L. Strike, you'll get rho upon 2 pi epsilon naught L. This is the electric field strength due to a line charge. I mentioned that it can be simpler, and I'm going to show you the simpler method using Gauss Law. So let's begin with what is meant by Gauss Law. What Gauss Law states is, if you've got a charge over here, and you create a surface, a Gaussian surface. Don't be mistaken, this surface can be of any shape, but there's a reason why we choose this shape. He said that if you were to define a shape, in this case a spherical shape, if you sum up the E dot ds, what do I mean? That means this is the surface area. I'm sure that you have learned in your math that every area has a normal vector. So if you take the electric field strength at that point, multiply dot product of the small little area vector, if you sum up this across the whole surface, that will be equal to the charge enclosed divided by this. Very neat expression. Let's apply this to a very simple situation, which is a point charge. If we draw up a Gaussian surface that's spherical, because of the symmetry, the E at all points over here will be the same, so I can bring out E, which is a constant. And can you see that E will be equals to Q upon 4 pi? Why so? Because this area over here is a sphere. So it will be 4 pi square, 4 pi r square. If we bring this down, it will be exactly the formula that we did just now. So the reason why we choose a Gaussian surface like this and not like this, which you can as well if you do up all the integration, it will give you exactly the same, which is Q upon epsilon naught. Because there is regularity, there is an expression for the area of a sphere. That's why we choose a sphere. And the E at all points on the sphere is the same. That's why it is the reason why we choose that regular shape for the Gaussian surface. Next one, which is this one that we derive over here. Line charge. I choose a Gaussian surface that is a cylinder. Why is it a cylinder? Because we know for sure that at all points over here, the E field will be the same. So therefore, the integral of E dot ds, which the field will point outwards, which is Q upon epsilon naught, will be again E times the integral of the surface, which is equals to the charge density times the length of this surface that we choose. Probably I choose another one, x naught, and I call this L. There's a reason why I do it this way. Fearing that you'll confuse you, I'll explain later. So this will be rho x naught upon epsilon naught, and the area of this will be E 2 pi L times x naught. And I can cancel with x naught. If you shift the 2 pi L over it, will be exactly the same expression over here. Now, let me explain. Why do I choose x naught? Why do I write this as x naught? Because if I write it as L, you get confused over the L over there. So that's why I choose x naught, and I want to use the same symbol L for the distance from the line charge. As you can see, much neater, much easier, but only possible if you realize, you might have realized, only possible if you have the field strength or some form of symmetry. They can choose a Gaussian surface that allows you to use to choose a Gaussian surface that allows for E field to be the same at all points on the surface. That is only possible if using Gauss law is only possible if you have this kind of scenario. Now, in situations where you don't have any form of symmetry, then no choice. you have to go back to the first principle, which is that. And that's why we need to go through that, because that is true for all situations. That method is applicable for all situations. This is only applicable for certain situations. All right. Now, what other situations do you need to know how to use Gauss law on? One very classic case is the case of a parallel plate, which is something that is very interesting. I'll show you why. If you have a charged plate where the charge has a charge density of this, this is charge per area, not length anymore, but per area. If I choose a Gaussian surface like this and like this is area A, it will enclose a certain area A over here. So integral E ds, because the field only points in this direction, we are talking about infinite plate, where it extends infinitely. So this one will be E times A, because E is constant at all points over here, so it will be just E times A, equals to rho times A over epsilon naught. Cancel, cancel. Now what is interesting about this is that the electric field does not depend on distance. That means even if you stand 1 million kilometers away, if the plate is infinite, your field strength will be exactly the same as if you were to stand 1 meter away, which is really quite puzzling if you think about it. That the field somehow cancels off, so that the vertical component will always be independent of the distance. But of course, the difficulty is to get the infinite plate, which is not possible in real life. Infinite, by the way, it is something that is very conceptual. It is something that is relative. To an n, a plate that is the size of this table will be infinite. But to us, probably we need a bigger plate. To planets, you need an even bigger plate. So it is a very relative kind of situation. Therefore, just a quick summary. What have we done up to now? By now, you should know how to use the k cubed upon r squared sum up using integral, and a very classic example of the line charge. You need to remember Gauss law, which is this, and apply it to the case of a point charge, a line charge, and a parallel plate, the case of a plate over here. Hang on, I think I realized that I made a mistake, a small mistake. It should be 2 area over here, so it should be 2 over here, because there are 2 areas where the field comes out from. Now the next thing I'm going to go into is a little bit of further integration. So I'm going to show you that how this can be done. Oh yes, probably one more case before I go on to potential. Now, in fact 2 more cases. So if we got a situation where this has charge per volume. So the charge per unit volume is a constant, and it's a solid sphere. So how do I find the field inside here at this point R when this is R naught? So the way to go about this is rather simple. Again, you use Gauss law. E dot ds equals to Q enclosed by the surface over epsilon naught. So what you do then is that you have E, same thing, 4 pi r squared equals to the Q enclosed, which is 4/3 pi r cubed times rho. So the 4 cancels off, and if you work it out, the pi cancels off, the r squared cancels off, leaving you with r, it will be rho r divided by epsilon naught divided by 3. So therefore, you got a case where the electric field strength varies like this, and then before it drops off after r. Because after r, it behaves as a point charge, it goes down with k cubed on r squared. So this is the case where you have a charge density that is constant. Now, how about a case where the charge densities vary with distance? So how does that work out? So therefore, if I have a case where I have R, same thing, I want to find the field strength at a distance R away. Total charge is Q, but the charge densities varies with, let's not use K, let's use alpha so that we don't mix up with the K. So it's alpha R, a constant times R. So same thing, E dot ds equals to Q enclosed divided by epsilon naught, E 4 pi r squared equals to Q epsilon naught, therefore. But the challenge over here is that Q enclosed depends on R. So we got to find out how to find the charge enclosed. Now, for this, we need to imagine shells. This is a shell of radius r and thickness dr. So the volume of this shell is 4 pi r squared dr. So the small charge of this shell will be 4 pi r squared times alpha r dr. It'll be the volume multiplied by the charge density. So if you integrate this from 0 to r, this will give you the Q enclosed. This will be 4 pi r cubed. In fact, this is r3 already, so it will be r4 divided by 4. So it will be pi r4 alpha. Prolong that in, this will give you pi r4 alpha divided by 4 pi epsilon naught r. You cancel away this will give you the expression for the electric field strength. Alright, so it's Gauss law but in a different context and in a different way. Alright. Well, the next thing I'm going to show you is how to work on potential and the concept of potential. So what exactly is potential? Let me explain to you first. Then I'll show you how to derive potential from this. Now, let's work from, if I were to have a mass over here, this is the gravitational force, this is dr. Do you agree that if the gravitational force were to work or to pull this object down towards itself, it will reduce the potential energy? Just like if I were to put this down towards the Earth, it will reduce the energy of the system. That's why there's a minus. So F gravitational force is minus du dr. If I were to divide both sides by m, can you see that this will be the case, and this is gravitational field strength. And this quantity is what we call potential, which is equals to potential energy per unit mass. In the context of electric field, Fe will be equals to minus du dr, but U over here is the electrostatic potential energy. So same thing, the form for field strength is equals to minus dV dr, but this is electric potential, this is gravitational potential. So first thing, you need to remember that potential is defined as energy per unit charge, this energy per unit mass, and the field strength and the potential are related by this. Why is this important? Let's take a look at this expression. Now, or probably you look at an expression that's simpler. Let's start off with the case where you have a charge Q over here, and we know that the field strength over here is KQ upon R squared. So since E is equals to minus dV dr, which is equals to KQ upon R squared, can you see that dV minus d, or rather, this KQ upon R squared dr will be the expression. If I integrate this from 0 and infinity to a potential at R, this will be V, and this will be just KQ upon R, which is the expression you'll find in any textbook in the world. So this is the expression for potential due to a point charge outside of it. Now how do we apply to this case, say for example? Let's start off with a case that we have up here. So this is a positively charged sphere of uniform charge density, and we got E, which is equals to minus dV dr is equals to rho r upon 3 epsilon naught. So dV integral minus rho r 3 epsilon naught dr. Now potential will go from, say, okay, if radius is 0, it will be a V naught at the center. It is not 0, it is a certain value, and to when it is at R and an unknown potential. Probably we don't integrate from that point. How about integrating from R naught to V naught? That means this V naught is the potential not at the center but at the surface, and there's a reason why we do it at the surface. I'll explain to you why. So therefore this will be V minus V naught is equals to rho r divided by 3 epsilon naught dr integral r naught r, which is going to be integral of rho r squared divided by 6 epsilon naught r. There's a minus over there, and there's a minus over here, and you go r naught r. So if you plonk this in, this will give you V minus V naught is going to be equals to minus rho squared 6 epsilon naught r squared minus r naught squared. Now, the potential at the surface of this thing over here. Remember that the potential at the surface of this thing over here, you can treat it as a point charge, and we got the expression over there is KQ upon R. which is going to be equals to Q upon 4 pi epsilon naught R. In this case, R naught. So you just have to plonk it into here. Q upon 4 pi epsilon naught R naught equals to minus rho squared. Actually, is there a rho square? No, no rho square. It's just rho. R squared minus R naught square plus Q upon 4 pi epsilon naught R naught. Yep. And if you realize, if I were to set R to be equals to 0, what do I get when I set R to be equals to 0? When I set R to be equals to 0, let me bring this up. V equals to minus rho 6 epsilon naught R squared minus R naught square plus Q upon 4 pi epsilon naught R naught. If I were to set R to be 0, I'm finding the potential right at the center, which is rho R naught square upon 6 epsilon naught plus Q upon 4 pi epsilon naught R. So what I'm getting over here is basically a value for the potential right at the center, which is actually higher than the potential over there. So a quick recap. What I'm applying and what I'm trying to show you is how this applies to different contexts. We apply to point charge, we apply to a charge which has volume, and then we're trying to find the potential inside and how this mathematics works out. And you always choose these limits against, you choose a reference point where you can actually derive an expression for the potential. That's why I chose R naught, which is at the surface, and V naught at the surface. So that's the reference point. Then I work inwards into the unknown. Okay? So this is basically what I want to go through with you today. The idea of electric field and Gauss law. So we'll stop here today, and I'll send you some assignments or questions for you to try. Very soon I'm going to select some papers from the past SPHO for you to try and just have as a stimulus for you to think about how these questions can be solved. All right, thank you.